Okay, well, thank you all for attending. I'm Seth Chandler. I'm a law professor at the University of Houston Law Center, affiliated with its Health Law and Policy Institute, and thank you for joining me on this October 2020 day. I'm going to be talking about a very applied topic, which is the costs of equality, which focuses on the effects of, come on. Okay, so there we go. Okay, next slide. Which focuses on the effects of machine learning on concerns about equality. And we see that all the time these days. We see decisions being made or influenced at least by machines with respect to incarceration, admission to university. That was a big topic in the UK recently. But basically, anytime you've got a machine or a person behaving like a machine, making a decision, the issues that I raise here are going to exist. And I'm going to show how Wolfram Language, particularly optimization, machine learning, and visualization, can help us understand what's going on in these settings and think about the advantages and disadvantages of trying to correct for whatever inequalities are created by the machine learning system. I should add that there are two files that are attached to this talk. The first is the data that I'm using, and the second is a copy of this notebook, so that if you don't get something, it's definitely available to you. All right, so instead of giving a very code-laden talk, there is tons of code here, but what I instead want to do is give an applied talk in which I focus on a particular example, which is one that has been controversial, which is the use by Broward County in Florida and a company that it hired called Compass to try and make recommendations about whether people should be released from prison based on machine learning algorithms. And so I'm going to focus on that data, but you should understand that the principles that I'm using apply to all sorts of forms of machine learning, and so that there's a broad set of theory that's being used here. All right, so we've got our data, and I'm sucked it in, and we've got this data, which is actually a simplified version of the data that was originally used, but for purposes of what I'm doing here, I actually think it's useful for pedagogic purposes to just stick with simplified data. We're going to do a little bit of formatting of the data. And you'll notice, by the way, that I'm going to make fairly extensive use of resource functions, which I think are the greatest things since sliced bread. Some of these are, as at the moment, unpublished resource functions. Those are things that I've looked at. If you want them, you can find them on the website, the Wolfram Cloud website for me. Others are published resource functions. But anyway, I actually make fairly heavy use. And what we're going to do is we're going to separate our data into what are called minorities. That's a sort of an American term for ethnic racial groups that in the overall population constitute a minority, such as persons of African descent, Asians, this construct called Hispanics, Native Americans or Indians, other indigenous people. However, for the imprisoned population in Broward County, they're actually a majority of that population, but nonetheless, I will refer to them as minorities, and I will refer to everybody else as majority. So we're taking a look at this data here, and we've split it up into majority and minority. And let's get forward again. Okay. All right. So what would the world look like before machine learning? And it would turn out that about 55% of the population who is exits incarceration remains law-abiding for the period of time that was measured. And so if you didn't have machine learning, you might guess that, well, everybody's going to be law-abiding. That's the best guess I can make. And therefore, if you let everyone out, you would have a lot of false positives, and you'd be having 45.5% in inaccuracy costs. But minorities and majorities would be treated equally because everybody would be let out. Or you could try to say, well, I'm going to be random about it, and 54.48% of the time I'm going to let people out, and 45.5% of the people I'm going to keep people in. Again, that would be racially neutral, but you'd have even higher inaccuracy costs of about 0.496, assuming that you weight false positives and false negatives as a 1. So that's what the world looks like in some sense without machine learning. Lots of equality, but pretty high error costs. All right, so let's do, though, some machine learning. And we're going to do a traditional thing of splitting the data into training sets and test sets. And I'm going to have minorities and non-minorities. I saved this in case something broke. And we can have a composite training and test set. And we're going to train the models on all the data, just on minorities and just on non-minorities. And so we get an association of these groups to various classifier functions. Again, I export that in case something blows up. What we then want to do is develop classifier measurements that look at various properties of our classifiers on the test sets for minorities and majorities so that we can see how we do. And basically, again, we're going to get an association of various groups to these classifier measurement objects. And if we barrel down, we're going to see the key result here. And this is what has people upset, and it's definitely worth considering. So if we look at how our model does on minorities versus non-minorities, what we find is that, for example, the true positive rate, the models are essentially equally accurate on each of these groups. And actually, the models do a little better on the minorities. But what we see is that the true positive rates are higher for the majority than for the minority. That is, of people who would not recidivate, if given the chance, a higher fraction are let out of majorities than minorities, and of people who would not recidivate, or, I'm sorry, who would recidivate if left out, we find that we're letting out a high fraction of majorities anyway, whereas we are confining a larger fraction of minorities. And so one of the key results and one of the things that has people upset is, hey, this machine learning model seems to be biased. It's saying of minorities who actually would abide by the law, it is not letting them out as at higher rate as it is for majorities. So the question is, why is this happening? That is, I'm not aware that the people at Wolfram Research cleverly biased their machine learning algorithms so that whenever it saw race, it discriminated on the basis of race. They didn't do that. And it's not that the model is less accurate on minorities. And it could be, well, the machine's just doing the right thing. Minorities recidivate more frequently. They have a lower incidence of the law-abiding class, except that has a hard time explaining why we have these two phenomenon of true positive inequality. Minorities who would be law-abiding if released are recommended for parole at a lower rate. And we have false positive inequality. This is sort of the white privilege problem of people from the majority who commit crimes are being recommended for release at a higher rate than minorities. And so there's been a big controversy and rebuttals and sur-rebuttals and scholarly papers looking into this. And I thought this would be a good opportunity for Wolfram Language and Mathematica to try and figure out what's going on. So let's see, and I do have an answer as to what's going on. In general, we need to think about machine learning and utility functions and thresholds. So the idea here is what do classifiers generally do? In general, they develop probabilities, a distribution over potential output classes for each individual. And they'll say, for this particular prisoner, we think it's 40% likely they'll recidivate and 60% likely they'll law abide. And so if you weight a false positive the same as a false negative, then the choice of what the classifier should do in order to maximize expected utility is quite clear. It should say, well, it's more likely than not that they're going to abide by the law, so let's let them free. And so, however, supposing a false positive, the Willie Horton story, for those who remember that, of the parolee who goes on a murder rampage, that's a pretty heavy score. And yes, we'd prefer to let law-abiding people out, but being locked up in prison, this person says, is not as bad. And so if that were the case, you would maximize utility by predicting recidivate. And so this is a little bit of the math of it. We can abstract away. We can expand this math to multi-class scenarios. We can come up with a formula. And this is just basic use of Wolfram Language algebra. And so what you end up at the end of the day is to realize that there's essentially a one-to-one correspondence between the ratio of disutility placed between false positives and false negatives and the probability threshold that you want to see before you let someone free. And so what you can therefore do is think of not just a single measure of false positives and false negatives, or a single confusion matrix classifying people based on the reality and the prediction, but rather a trajectory of confusion matrices and statistics derived therefrom, in which you base it on a utility function in which different utilities are accorded to false negatives or false positives, or equivalently, a different threshold is required of probability before you let someone free. And so what we're now going to do is actually see that. So for example, here what I can do is, here is our confusion matrix done with the Wolfram convention of reality being on the rows. And here are little labels of true, negative, false, positive, all this stuff. And as we change our threshold, we can see the confusion matrix start to change. Various statistics of those confusion matrices start to change. Or we can change the incidence of law-abidingness in the population. Again, see changes. We can see what happens to inaccuracy costs as I change the cost of a false positive or a false negative. And the main purpose of this particular manipulate is to just fortify your intuition that, in fact, there's a trajectory of confusion matrices and associated statistics that varies as I vary the threshold requirement for letting someone out, or equivalently alter the utility ratios of making various forms of mistake. All right, and so we can see, for example, what effect that has on these statistics. So if I, for example, were to lower the threshold to let a minority person out, let's lower it to 0.3, what we can see is that there is a change down here in the associated statistics. And now, in fact, by doing that much, I've let minorities, the false positive rates and true positive rates, be higher than they were for majorities. You'll also notice that I tried to mask the fact that my code was slow by using little buttons here rather than having sliders. And so what I developed was a resource function that actually can enable this sort of computation more quickly. And this is one of the resource functions, and I just had a very good discussion with Campbell-Nald about how this might be put more directly, this functionality might be placed more directly into things like classifier measurements. But what's going to end up here is an interpolating function that goes from a parameter, which is a threshold value, the threshold we require to let someone free, to a confusion matrix. Okay? So we've got that, and once we have that, we can have all sorts of fun. So one thing we can look at is what's called a receiver operating curve, usually presented in 2 dimensions, but I actually think that has a flatland effect of losing some valuable information. And so this is a 3-dimensional receiver operating curve in which we see the trajectory sweeping out of false positive rates, true positive rates, which is sometimes called recall, as we vary the threshold that's required before we let someone free. And these red dots and blue dots represent the points at which we have an intersection. And so as I vary the threshold, you can see those red dots and blue dots moving. And this is basically capturing the notion of disparate treatment of minorities and non-minorities. We can also see this in a more traditional way if we simply look at it from the top. And that's a much more traditional view of the receiver operating curve. But what it shows is again this notion that although the model actually works better on minorities than it does on non-minorities, and I apologize, there's some issue with the coloring here, which after the talk I will sort through. But what you can see is that even though the classifier is not working quite as well on majorities, nonetheless, because of higher incidence, they are having a higher false positive rate, higher true positive rate. Basically, they're being let out. And we could also see this, if you didn't want to go through all that, in a more traditional form here. So what we might want to do is to adjust, supposing we think this is unfair. It's unfair, it's wrong that if I take a person who is a minority, and if I let them out, they would be law-abiding, I should let them out just the same as if they were a member of the majority. And so one way to do that might be to use different thresholds to say that for a minority, I'll let you out if I think there's a 30% chance you'll be law-abiding. For a majority member, it's got to be 60%. The disadvantage of doing it that way is I'm going to make my classifier less accurate than it was before. I'm going to basically deliberately sabotage the accuracy goal of the classifier in order to attain greater equal treatment among various subgroups. So we have a trade-off here. And one of the questions is, how do you go about weakening a classifier? One way would be to change the thresholds, as I was suggesting in the previous slide, but there are occasions in which changing the thresholds cannot attain various metrics of equality. And let me just go back to this graph here that I had earlier. Come on. Previous slide. Right. So if I wanted, for example, this is the manipulate I want. All right. If I wanted the true positive rate for minorities to be the same as the true positive rate for majority, so at least I was treating people who would be law-abiding the same, I could simply lower the threshold for minorities to some extent. And if I do it just right, there we go. We've got approximate equality there. And so I can achieve that metric of equality. But if I confine myself to this ROC curve, there's nothing I can do other than get very, very low thresholds or very, very high thresholds, which are very costly, to get equality in both false positive rates and true positive rates, which is what some advocates have called for. That's called an equal odds measure. And if you look at the end of this paper, I've got a bunch of resources. The leading paper is the one by Hart and Sribo, and that's the term that they use, and they also seem to be advocating for equal odds as a metric. So in order to get inside the ROC curve, we need to actually weaken the classifier, and there are various ways of weakening the classifier. One is to blur the data. If the data isn't as good, the classifier can't do as good a job, and so maybe you bin the number of prior arrests. Or maybe instead of taking a person's real data, you just draw a person randomly from the set of all prisoners and you use that. And so you can see here that we can weaken the ROC curve for a classifier by blurring the data. And you might think, well, that's absurd. But in fact, I happen to know that in Houston, where I live, this is the system that's used to admit people into various schools with advanced curriculum. They basically bin data to an extent that they get greater equality in true positive rates and false positive rates among various ethnic groups and their success in these more accelerated programs. Or another thing you can do is flipping. The idea is to say, well, our classifier predicts that you're going to be negative, that you're going to recidivate, but some random fraction of the time, we're going to flip that to a positive result, and a potentially different percentage of time, we're going to flip a positive result to a negative result. And so by doing it that way, you can move your classifier into the interior of your data set. So here, in fact, I'm trying to get the minority. We got to do, and if I jiggle the threshold a little bit, all sorts of fun things can happen. But I can basically achieve equality through a combination of flipping and adjusting the threshold. So that's another mechanism for achieving these more sophisticated methods of equality. And finally, and this is what the Hart-Sribo group recommended, is to use a stochastic threshold, to not say it's always 50%, maybe sometimes it's 30% likelihood that it's required to get out. Other times it's 70% likely to get out. And you can kind of see how this works here, where if let's set the majority, let's sync the majority. Did I sync it? Come on, sync. Okay, so that's my majority, that's my target. And what do I have to do? Well, let's see, if I weaken this, and then I weight, I need to weight this one some more. What do I have to do here? I want to move this up here. In any event, if I do this enough, you can always get the big red dot to line up over the little blue dot and achieve equality. And one of, the case for doing this by a computer, you just saw made by the fact that I didn't do a very good job trying to do it by hand. And in fact, in one of the slides, you'll see me using some optimization techniques to try and get the two dots to fall over each other and achieve these other metrics of equality. The problem is that every time I do that, I am weakening the accuracy of the classifier. And so this manipulate here is going to show how much I'm weakening it in order to achieve equality. And so in fact here, I guess I basically solved it. And you can see that the total inequality costs went up from 616 when I just left things alone, and they've gone up to 716 as a result of my efforts to achieve equality. Now, is that a good thing or a bad thing? I suppose it depends on the context and how much you value equal treatment. The only point that I want to make here is that there are, in fact, costs of achieving that particular metric of equality. And, oh, here's the optimization problem. All right, so we got compiled functions using the new compiler, the old compiler, blah, blah, blah. And since I'm running out of time, let me just show you an end up result here, which is, I think, if you want one picture, here's the picture. So these are different metrics that you might want to use in determining how to administer a test, how to administer a machine learning algorithm. And here are the costs of equality that result, costs of the inaccuracy costs that result. And, how do you minimize inaccuracy costs? Well, you tell the machine, minimize inaccuracy costs, and that gets you the lowest result. What's the worst thing? It's this equal odds measure where you're trying to get both the false positive rate and true positive rate to be the same. And then there are various intermediates here. And again, does going from 0.33 to 0.39, is that fatal? Should we give up on our goal of equality? That's sort of a decision that's somewhat above my pay grade, but at least we've identified what the cost might be. The issue comes, though, if you insist on equal odds, there is generally always going to be some intersection of classifications for which the classifier doesn't perform well, like maybe female Native Americans. We don't have very many of them in prison, so we might not have very good data. Or maybe it doesn't work very well on male whites over 60. And if we insist on the classifier being dumbed down so that it performs to the level that it does on the weakest group, we could have quite significant increases in inequality costs. And what the next segment of this does is, it turns out the classifier doesn't do very well on what I call hardened criminals. These are people who have more than 10 prior arrests. And so what I'm going to show here by the end of the day, after a lot of code, you can see the ROC curve on hardened criminals is nothing to be proud of. And we keep going down and we keep doing it, and you should read this in the paper and download it and study it at great length. But at the end of the day, you can see that moving up to equal odds causes an increase in inaccuracy cost from 0.33 to 0.55. And, you know, depending on what those units are, that could potentially be very troubling. All right, so what are the political implications of the research? It does suggest that maybe we you know, in law, there are various various theories that are approved for what in the United States is called affirmative action, basically giving certain forms of preferences to certain forms of historically underrepresented groups. Most of those legal theories have actually been rejected by the Supreme Court in its present condition. But this is suggesting that either incidence bias or weakness in classifiers might be a basis for granting some preference to disadvantaged groups to compensate for the problems of the classifier. But what it also does is, to me, it suggests a good deal of caution in going to certain measures of inequality, particularly the equal odds one that my friends at Hart and Sribo and the like are recommending. I think with that, here are some references. This is, as I said, if you want to read one paper, this is probably the paper that you should read. This is probably the paper that's closest to mine, but not nearly as good. This is how you can get in touch with me. And I will stop there and look at the chat. So, assuming I can figure out how to do this. Okay. Here we go. All right. So if I look at the chat, what I see is that no one's chatting.
Refresh the page.
Okay, refresh the page. All right. And also I'm going to share the screen somehow so that it captures the chat. Well, I'll just capture my whole screen. What the heck? Okay, so would different classifiers used by type of crime? Right. So the underlying data, as I remember it, may have some information on it on type of crime. It basically has distinctions between felonies and misdemeanors. And yes, I agree that letting a felon out might be much more significant than letting a shoplifter out, or drug possession and murder, as you say. I wanted to create a simplified pedagogic presentation here, and so I used the simplified version of the data. But the theories are all the same. That is, the fact that both the classifier works better on both minorities and majorities by adding certain forms of data does not eliminate the underlying problem that the classifier tends to perform differently based on racial subgrouping. And then you have the issue that I've raised, which is what are we going to do about it? Dave DeBroda asks, utility function and classify useful? And the answer is damn right useful. It's you know, critical to getting the kind of results that I'm getting. And so if you look at, I think, some of the resource functions that I've put up or will put up, they're adjusting the parameters of the utility function as sort of a way of changing the threshold of probability that's required. So I hope that's helpful to your question. If there are other questions, I'd be happy to entertain them in the chat. Otherwise, I think I'm going to turn into a pumpkin here. But if anyone wants to further discuss this, or additions or suggestions, is the solution getting more data? I suppose in theory, if one had infinite data, then any differences in recidivism that one saw would in fact be caused to some extent by race, and you might want to but what we find is that even if the classifier performs equivalently, that is, even if when viewed in 2 dimensions, the ROC curve is the same for 2 groups, nonetheless, you're going to see the problem is bigger than simply not having enough data. The problem is that if the incidence levels of the positive class differ by racial groupings, you will tend to get higher false positive rates and higher true positive rates in the group for which the incidence is higher. And that is, from many people's perspective, a problem. That is, the problem that I've identified here, unless you ended up with a perfect model on all subgroups, which strikes me as unlikely in most practical settings, the problem I've identified here will persist. Now, it may be that correcting it has lower costs in those settings, but this is not simply a problem of not having enough data. Yes, causality, you know, these classes do not presently understand causality, and to be sure, you know, the ideal solution would be to set up an environment in which people didn't commit crimes, and so you would give them education support and better family and better access to housing and all those other things that would tend to reduce crime. That's, you know, that problem is definitely above my abilities. Yes, so Dave asks, basically he wants to know about shouldn't there be degrees of recidivism? And in fact, again, the underlying data distinguishes between what it calls violent recidivism and nonviolent recidivism. And it has different subgroups for that. And certainly, I want to take a look at that and have taken a look at that actually. For my pedagogic purposes, again, I wanted to just abstract away those details and focus on the more fundamental problem, which is going to persist, which is that if there is a difference in incidence among the various groups, the classifier is likely to have behavior that many people find unpalatable. On the other hand, fixing that by modifying, for example, thresholds, will make the classifier less accurate, and less accurate classifiers can have big problems if you're now letting out people that are likely to commit serious crimes, or similarly incarcerating people who really would be just fine if you let them out, and you're letting them rot in prison at their expense and the expense of society. So there's some additional questions by Dave on measuring, I would say, the harm and getting better data. And you know, absolutely, I agree that better data might be useful in both making decisions and in doing classifiers. I'm limited to the data that I have and the data that Compass and the like collected, which is not perhaps as granular as one would like. And with that, I think I don't know if I have to do anything, Ed, to call this to a halt, but
Nope.
so magically make me disappear. Thank you all for attending. Thanks for your questions, and look forward to hearing from the rest of you at the conference.